702 and Cape Talk.
The Naked Scientist.
Chris, good morning to you.
Hey, good morning.
It is holiday year for school kids, and I'm delighted that our first caller today is a youngster interested in the wonderful world of science. So let's take a question from Alicia. Good morning, Alicia.
Hello, Chris.
Hello.
Why do you see yourself upside down when you look inside a spoon?
Yeah, okay.
Chris.
This is a terrific question, and thank you for sending it in, Alicia. If you look at a spoon, the reflective surface behaves like a mirror. So the first question, why do you see yourself? Because it's a reflective silver surface, just like a mirror, it's reflecting light rays back at you. But if you look at the surface of the spoon, you'll see it's a curve. And that bowl-shaped curve has an effect of working like what we call a parabolic mirror. When the light rays hit the spoon, they are reflected at you at an angle. And the curve means that they're reflected almost like it's focusing light. And so the light is focused onto a point just in front of the spoon, and then the light rays go through that focal point and begin to spread out again. So if you can imagine a picture, and the top of the picture sends a beam of light to a point going downwards in front of it, it then goes through that point and out the other side. What was at the top ends up down the bottom, and what was at the bottom ends up, when you see it, at the top. So it will have the effect of flipping the image and reversing it as well, because the light rays go through that focal point and come out the other side. We use the same science, actually, in some forms of astronomy, because we have telescopes that have a big parabolic reflector, and when the light comes in from a distant star, it goes through the telescope, bounces off the mirror, which focuses light just like a spoon, but hopefully with a little bit more accuracy and precision, to a focal point where the detector is, and that's how the telescope sees.
Wonderful. Thank you, Alicia. And if there are other youngsters listening, please do call in, or mom, dad, if your kids love science. Maybe they've got a question for Chris today. We've got so many people calling in today, Chris, which is fantastic. Johnny, just turn down your wireless for me in the background. I'll come back to you in a second. In the meantime, let's go to Irvin. Irvin, welcome to the show. What's your question?
Good morning. My question is why boiling water is so stubbornly hot. When I shave in the morning, I take some boiling water and I put it in the basin. Then I add cold water, at least as much, if not more. But I still can't put my hand into it. And it always amazes me. I've got to keep adding cold water before I can use it. And I just wondered if there's a reason for that.
Yeah, there's a couple of aspects to this, and it's a good observation. First aspect is that what you're calling cold water is probably water at about 20 degrees. So if you've got boiling water at 100 and you then put water at 20 in, actually it's going to meet somewhere in the middle when you put equal volumes in, isn't it? So the temperature isn't going to fall halfway, it's going to fall halfway between 20 and 100. So it's still going to be potentially 60, 70 degrees when you've put the equal volume of cold water in. So it's still going to be extremely hot, because we experience temperatures of above 50 as extremely hot and painful. The other consideration is that water has a very high specific heat capacity. In other words, you have to supply or remove a very large amount of energy from water in order to get the water to change temperature by just 1 degree. The specific heat capacity for water is 4.2 joules per degree centigrade or Celsius per milliliter. So in other words, you have to take away a very large amount of energy just to make a tiny amount of water change its temperature by a small amount. And if you've got a big bowl of very hot water, you've got to take away a lot of that energy to make it cool down, or add a lot of water at a much lower temperature in order to get that temperature to come down. And that's the reason why it seems to be so stubbornly hot in your case.
Chad, welcome to the show.
Hi, Sidis, how are you?
I'm good, thank you.
Good. I'd like to ask you a naked scientist question, right? With regard to black holes and the universe, we all know that black holes draw things into them, right? So I wanted to know, does that mean the universe is getting bigger or smaller?
Oh, hi, Chad. Well, the answer to this one is that on the scale of the whole universe, as far as we can tell, the universe is inflating. It's getting bigger, and the older it gets, the faster it grows. And we think that the phenomenon responsible for driving that effect is called dark energy, but we don't know what it is. This is a sort of counter pressure on gravity, which is trying to pull the universe closer together. So the answer to your question is that the universe isn't going to go down a giant black hole plug hole anytime soon, because the universe is getting bigger, and the bigger it gets, the faster it gets bigger. Black holes are gravitationally active, but they're gravitationally active in their part of the cosmic neighbourhood, and they're very common. There are lots of black holes out there. The centre of our Milky Way galaxy has a supermassive black hole sitting in it, but they are not going to make the universe collapse anytime soon.
Johnny, good morning. Go ahead.
I need to know if the possibility exists for trees to grow on rocks or stones, and if this is correct, what is the source of life in terms of water and nutrients, since rocks and on stones seem to be dry, considering the 3 states of matter, they seem to be in the solid state.
Oh, lovely question. Chris?
We've all seen this, haven't we? Trees and plants growing in apparently impossible places. And if you went and tried to plant something in your garden in an environment like that, it would never thrive. Yet in nature, these things find a way. The answer is that there are plants that are very well adapted to growing in extremely weird-looking places. They have a very, very well-developed root system. Often these plants also are very good at conserving water, so they're plants that are well adapted and evolved to grow on water-sparse soils or very sandy soils or very rocky soils. Often where you see these things growing out apparently from rock, the trick they're using is either the rock is broken and they've got roots that go down through tiny pores and cracks in the rock and they can tap into water deeper down, or the rock itself is quite porous, and you'll see this with limestone rocks where there's lots of little gaps in the rock, and by threading its roots down through tiny little sinkholes in the rock, the plants can access water that way. Or a strategy they commonly use is to have a dense mat of roots that spread out over the surface of a rock just below the thin layer of or veneer of soil on top of the rock, and they can access water in that way. But plants won't themselves grow out of purely rock. They need to gain access to water. That's the number one thing. The other nutrients that are there, minerals and so on, there's often enough fungus and other things growing in the thin layer of soil on a rock, and the fungi are what bring in a lot of the raw materials the plant needs, and then the fungus trades those with the tree or the plant for sugars. So the trees get their other supplies via fungi, and so as long as they're adapted to surviving in a low water environment, they can get a lot of the other stuff from the surrounding other microorganisms. And the chief source of energy that they get is the sun, and the other thing that they pull out of the air is carbon dioxide. That's the carbon source that they then use in order to actually grow the body of the tree, because the tree is made of wood, and wood is lignin, and this is a giant polymer, the chief ingredient of which is carbon, which comes from the air.
702 and Cape Talk.
The Naked Scientist.
Kahisa, good morning. Speak to Chris. What question have you got for him?
Hi, Eusebius. I know that Jupiter has multiple moons, and Earth only has one moon. And I know that the moon does affect the oceans. It does affect the tides in our world. So if Earth had multiple moons, how would our oceans be? Will they be more volatile, or how would, let's say, 5 moons? If we had 5 moons, how would that affect our oceans and our tides?
What a lovely question. The answer to this one is the reason the moon has such a profound effect on the tides on Earth is because relative to the Earth, the moon is very large. And the reason we have such a large moon relative to the size of our planet is because our moon was made by a giant collision about 4.57 billion years ago is how long ago we think it happened. Some people dub this the Big Splat. It was in the early infancy of our solar system, and there was 2 planets, and one of them notionally called Theia, which was about the size of Mars, that ended up on a very similar trajectory, and they slammed into each other. And that collision between the nascent Earth and Theia led to the ejection into the air around, or in space around the Earth, of a huge amount of Earth's crust material. And that crust material slowly coalesced to make our moon, and that's why the moon is thought to be exceptionally large. And because it's exceptionally large, it has a lot of mass, and because it has a lot of mass, it's very gravitationally active, and that's why it produces this tidal bulge. It pulls water on the Earth's surface closest to the moon and causes a heaping up of water there, and you get an equivalent bulge on the opposite side of the Earth as well, because the Earth's in the way between the moon and that side of the Earth, so the Earth moves more than the water does, so you get 2 bulges. On the other hand, if we had more moons, well, if they were all of similar size to our present moon, then they would all be gravitationally active, and they would all be trying to pull bulges of water in the same way that our present moon does. The water would obviously be shared out around the Earth over a bigger area, because instead of it being pulled from just one direction, causing it to heap up in just one place, it will be being pulled from numerous directions, and that would be more complicated to predict. But the key thing is how big these moons are, because it's the mass that gives them their gravitational influence on our planet, and that's what causes the water to move. So you could have hundreds of moons, but if they were tiny little specks, they would not make any kind of gravitational consequence, in the same way that we don't have a high tide because the International Space Station goes over. But if you do have a big moon, you do. So if you had lots of moons and they were very big, then you would have tides being pulled in all kinds of directions, and you wouldn't have these 2 high tides a day like we get at the moment. If you had lots of little moons, that effect wouldn't be visible, I wouldn't have thought.
Canelwe, good morning to you. Welcome to the show.
How are you?
Very well, thank you. How are you?
Good, thanks.
What is your question? Have you got a question for us?
Yes, my question is, what is the average atomic weight of silver?
Okay, there's a lovely question from an 11-year-old listener, Chris.
I think the question is, what's the atomic weight of silver? Without looking in the periodic table, I don't know. I don't keep the weights of all of the elements in my head. I'm sorry, you've caught me out with that
well
one.
Well done, Canelwa. A rare moment. Why does it matter, Chris, or why might that question be of interest to anyone?
This is of interest because when we build the periodic table of elements, which is that giant table you see on the wall of your chemistry classroom or your physics classroom, every element is a different physical entity. It's a different chemical. The atoms are different sizes. They have different numbers of protons and neutrons in the nucleus, different numbers of electrons orbiting around the outside. And that means the mass, because you've got more protons and neutrons, which are the massively active particles that make up the bulk of the mass of the atom. Well, actually, that's not strictly true, because it's the energy that binds them all together that gives the atom 99% of its mass. But we'll relate it to being the numbers of neutrons and protons. That mass, therefore, means that every different element weighs, in inverted commas, a different amount. And if we want to work out how much silver we've got, or how much hydrogen we've got, or how much cesium we've got, or how much sulfur we've got, then actually we do that by using what's called the relative atomic mass. And what scientists have done is they have weighed a certain amount of atoms of silver compared with the weight of an equivalent number of atoms of hydrogen. And so we know that in order to have the same number of atoms of hydrogen or silver, we have to weigh a certain amount more hydrogen, because there's far less of it, than in terms of how massive the particles are compared with silver, to get the same mass. Or we can therefore relate how many particles we're dealing with. And that's how you do it.
Tsepo, good morning to you and welcome to the show.
Hi, YouTubers and the Naked Scientists. My name is Tsepo Tamana from Monsteneria. Please, Dr. Chris, why is that whenever I go to the barber to cut my hair, as he cuts my hair, I always get a numb, tingly feeling on my left buttock? And it's something that I've had as long as I can remember. And I once asked the Naked Scientists website, and they said it's something to do with ASMR, which is Autonomous Sensory Meridian Response.
Okay,
no,
that's interesting.
I think we joked when you said he was cutting your hair and you felt pain in your buttock. I think we said, how long is your hair? It's like... But I don't think that's what you meant, is it? I have got a similar thing where if I pinch myself roughly on my flank to the left of where my breasts are on each side, then I actually feel pain, or the equivalent sensation on each side, on the tip of my elbow. And I think the reason for this is that when a person grows arms as an embryo, the arms bulge out from the side of the body, and they take with them the nerve supply from that patch or strip of the body surface. And all the nerves that flow into the spinal cord in the body, which bring in sensory information, they all plug into certain levels up the spinal cord, and there's often a bit of overlap from one area to another. And so if you stimulate one nerve that corresponds to one part of the body, if it's also got some connections into the adjacent body region, you can sometimes get some overlap of the sensation. So you get what's called a referred sensory experience. So you experience a symptom or a pain in one place, or a tingling in one area, but then you also experience a simultaneous tingling in the other area it's accidentally also connected to. It is possible that there are some kind of neurological overlap in yourself between the nerves that are supplying sensation to one part of your body and another part of your body. The other possibility to bear in mind, of course, is that if you are putting yourself in a certain position or posture, bending your neck in a certain way so that you can have your hair cut I don't know, they often angle your head over to one side to do a part of it, don't they? If that's putting your neck in a certain position, it's possible that you could also be pushing on some nerves in your neck or your spine. So if you can put your head in a certain position and reproducibly produce a symptom, that's another possibility. Or you're putting your back in a certain posture and it's tweaking a nerve that does supply the buttock region. So I think that would be my speculation as to how you would explain what you experience.
Very interesting question, that one. Tembani, good morning.
Morning, CBS. How are you?
I'm good, thank you.
My question is, why is it that when you are exercising or when you are running, your front part get to sweat more than the backside? Because when you are facing the wind, it's supposed to be much more cooler in the front part. But then I've realized that when I exercise or when I run, the front part, your chest, your stomach get to sweat more than the backside. Why is it like that? I'll
Well,
listen to the radio.
That's a very interesting question. I don't know, so I'm going to speculate, okay? It's possible, well, we know that the distribution of sweat glands on a person is not uniform across the body. Some areas of the body have much greater sweating capacity than others. That's the first point. The second point is that it may be that you just notice it in some places more than others, and it may be that it evaporates better from one surface depending upon what you're wearing than others. So if you're running, you're leaning forward a bit, so your shirt might gather some water but then tip away from your skin, and the supply of heat, which is evaporating the sweat off of you, therefore is a bit less on the front than on the back. I don't know the answer to that question. I'm going to have to go and do a little bit of research. It's possible that it's just down to how many sweat glands you have in different areas, but I'll find out and I'll come back because I'm intrigued with this question.
David, good morning.
Good morning. Chris, I have a question about water. We know it's a known fact that you cannot compress water. Now, how come it can expand when it's frozen?
Hi, David. Well, they're quite different phenomena. When water is in its liquid state, you're right that effectively it's incompressible. You can make it a tiny, tiny, tiny bit smaller, but it's effectively incompressible. Water can change its volume, though. If you make water hotter or colder, it will thermally change its size. That said, it's not on the scale of when water freezes. And when water freezes and becomes ice, it becomes significantly bigger and therefore much less dense, which is why ice floats. But the reason it actually changes its volume so dramatically is that if you were to zoom in with an incredibly powerful microscope at liquid water, you would see water molecules which are shaped a bit like miniature boomerangs, with an oxygen at the centre, apex of the boomerang, and a hydrogen atom sticking out where the arms are. And those water molecules are this sort of warped, bent shape, and they all have to plug together. And it just so happens that for energetic reasons, the water molecules can snuggle up a lot closer to each other when they're making associations between the molecules to make a liquid. But when the water freezes, the way it organises those molecules is much more energetically favourable if they adopt a much more open, distant structure. And it's because they are in a more open structure with greater separation between the molecules that ice takes up a lot more space than liquid water. So it's actually all to do with how the water molecules organise themselves in three-dimensional space between those two different physical states of matter, the liquid state and the solid state. And that's why you get that very dramatic difference in volume.
I think we can squeeze in one or two more questions. Sam, you've got an interesting one for us. Go ahead. What do you want to ask?
Hello.
Hello there.
Yes, please. My name is Sam. I wish to find out from the naked scientist, why do animals not run in a straight line?
Why don't they run in a straight line? Yes, and this is a brilliant question. And actually, researchers have solved this in recent years. Researchers at the University of Swansea actually have been looking at this question. The way they solved it was to go into the bush and they put collars on animals that could measure accelerometry data. In other words, how fast an animal is turning. And if you know how fast an animal is turning, you know how much force it has to generate to turn. And because you know how much the animal weighs, you can therefore work out how much energy it's expending, because every time it turns, it's got to use energy to accelerate in a new direction. And they were looking at big animals and small animals, because what they found is that the best strategy to get away, if you are smaller than the thing pursuing you, is to put in loads and loads of turns. Because every time you turn, you're using energy, but so is the person or the thing coming after you. And if they've got a bigger body than you, every time you turn, they have to turn. They have to use more energy than you do to turn. And if they're using energy faster than you are, they're going to get tireder quicker than you are. And therefore, you're going to stand a much greater chance of getting away. So the best strategy is, if you're being followed by something bigger than you are, is to put in as many turns as you possibly can. That was the discovery. On the other hand, if you're huge, the best thing to do is not to turn at all, but to run in a straight line as fast as you can to get away and hope that they get more tired more quickly than you do. And that is the very strategy that's used in the African bush and other parts of the world where you've got prey animals and predatory animals. You will see the smaller ones turn as fast and as often as they can to tire out the pursuer before hopefully they get tired and before they get caught.
Ayanda, good morning to you. What's your question?
Good morning, Eusebius, and good morning to the doctor. I would like to find out about the problem of the palpitations. What is as a person who's been diagnosed with, like I'm on a chronic medication for palpitations, but I'd like to know what are the safe numbers, like when they test you with the machine that they use for BP and the pulse. What is the safe number for a person to be not to panic, because I have different information. I get different information from people in the health, like the nurses, and when you go to the doctor, you get a different picture.
Okay, I get the question. Yeah, a safe number or range of heartbeats, I don't know, perhaps per minute or so, Chris?
The question concerns this phenomenon dubbed palpitation. Now, palpitation is a medical word that means a sensation that your heart is beating either very forcibly, very fast, or with an irregular rate or with extra beats. Now, in a young, healthy, fit person, extra heartbeats, also known as ventricular ectopics, are not uncommon, and they're also usually not harmful. If you're an older person and you suddenly start to suffer irregular heartbeat, or you sense that something is not right, or this periodically comes and goes, something effectively has changed, then that requires investigation. And just to be sure that nothing's wrong. The heart has what's called a myogenic rhythm. The heartbeat is generated by the heart muscle itself. It's the electrical discharge of the cells that make up the heart that means the heart beats of its own accord. And in fact, if you take cells that are going to develop into a heart in an embryo and put them in a dish with the right solution, they will just beat all on their own. They don't need any other stimulus to do that. And so the heart knows how to beat. It knows how to beat at the right rhythm, and it follows the pattern set down by a specialised region of the heart, which is called the sinoatrial node, and that's the pacemaker that's naturally in your heart, and it sends signals to the rest of your heart to follow. Sometimes, if the conducting system in your heart goes wrong and those signals are interrupted, or a different part of the heart tries to take over as the pacemaker, you can start to introduce these irregularities. And if that's happening, usually it's easy to deal with, it's easy to control and can be well managed, but if it is a new thing, it can be a sign that something's wrong and it should be investigated. And I would urge someone to go and get it checked out just to make sure that it's just a variant of normal.
Thank you, Chris. Stunning edition. As always, thoroughly enjoyed it. And we had so many more questions we couldn't get to. We'll do it again next week.
I'm
Have a
looking
beautiful
forward to
7 days ahead.
All right then, Eusebius. Thanks, everyone.
Cheerio.